So we'll see about 8086 microprocessor. Before going into the architecture of 8086, so we'll see what are the general specification. It is a 16-bit microprocessor. It has 20 address lines that can address up to 2x20 memory locations, that is 1 MB. So any processor that has n address lines, it can address up to 2 power n memory locations. It can support up to 64K IO ports. It has multiplexed address and data bus, which is specified as AD0 to AD15 and a separate address lines as A16 to A19. It requires single phase clock with 33% duty cycle to provide internal timing. 8086 is designed to operate in two modes of configuration, that is minimum mode and the maximum mode. It can prefetch up to 6 instruction bytes from the memory and it can queue them in order to speed up the instruction execution. It requires plus 5 volt supply and it is a 40-pin dual inline package IC. We'll see the block diagram of 8086. So you could see two important blocks. One is the bus interface unit, which is at the top, and the second one is the execution unit, which is at the bottom. You could see here the bus interface unit consists of the segment registers, which is specified as extra segment, code segment, stack segment, data segment, and along with that it has instruction pointer. You could also see to that it has a 6-byte instruction queue, and this also is connected to a memory interface where it will communicate to the outside world. And this bus interface unit, the very important function is it is the formation or the 20-bit physical address calculation. And coming to the execution unit, you could see here all the general purpose registers, which is defined as AX, BX, CX and DX, which in turn it is divided into AH, AL, BH, BL, CH, CL, DH, DL, which is nothing but the L represents the lower order register, H represents the higher order register. It also has stack pointers, base pointer, source index and destination index. It has arithmetical and logic unit which performs all the arithmetic and logical operations. And you could also see a flag register, which is a 16-bit flag register, and this flags will get affected after the operation of arithmetical and logical operations. And I have put down the functions of bus interface unit and execution unit. The function of bus interface unit is to fetch the instruction or data from the memory, write the data to the memory, write the data to the IO port, or read the data from the IO port. Similarly, the functions of execution unit are, it will tell the bus interface unit where to fetch the instructions or the data, as well as it decodes the instruction and it executes the instruction. The execution unit contains the control circuitry to perform various internal operations. A decoder in the execution unit will decode the instruction fetched from the memory to generate different internal and external control signal which are required to perform the operation. These are the registers of 8086 which I have told you already. So these AX, BX, CX and DX, you call it as general register. You have index register which is SI and DI. You have pointer register which is base pointer and stack pointer. You have the flag register where you have, it's a 16-bit flag register, and out of which you could see a 9-bit positions of filled. And you have the segment registers, which is code segment register, data segment register, stack segment register, and extra segment register. And this is the architecture of 8086 as I mentioned earlier. So this is the just a grasp of it, where you could see what are the registers present over here, which just now I told you. And this general purpose register, quite briefly, this AX is a accumulator register. Of course, you know this is divided into AH and AL. So the basic function is it performs arithmetical, logical, and even it is used for data transfer. When you are operating on 8-bit data, AL will act as an 8-bit accumulator, and when you are operating with the 16-bit data, AX will act as an accumulator. BX is the base address register. CX, normally it is called as a count register, where this can be used for iterative code segment using the loop instruction, or you want to perform any repetitive operations in, especially in the string manipulation instruction, with a repeat command. And even this can be used to store the count, especially in the CL register, for how much time the bits has to be rotated or shift when it comes to the rotate and shift operation. And DX is the data register, and this is normally concatenated with the AX register to form a 32-bit register, where you can perform some multiplication and division operation. And coming to the source index register, it can be used as a pointer for addressing the data in certain addressing modes. It can be used as a source in some string processing instructions. And it can be used as an offset address which is related to the data segment. Similarly, the destination index register can be used as a pointer in addressing the data. It can be used as a destination in the string operations. It can be used for the offset address relative to the extra segment. Coming to the base pointer, it is primarily used to access parameter passed via the stack, and this can be used as an offset address relative to the stack segment. Coming to the stack pointer, it always points to the top of the stack. Offset address can be utilized with this stack pointer, which is related to the SS. It always points to a word, that is byte at an even address. Coming to the segment register, which is present in the bus interface unit. So you have 4 segments, which is code segment, data segment, extra segment, and the stack segment. So these segment register will point at the segment containing the respective segments. So for example, if you take code segment register, it will point to the segment containing the current program. Data segment, which will point where the variables are defined. Extra segment is an alternative data segment. It does the same thing as the data segment register. Stack segment, it will point to the segment containing the stack. This segment register can be used as a general purpose register for which can be used to access any memory value. The CPU makes a calculation of the physical address by multiplying the value present in the segment register by 10 in hex, and this will be added with the general purpose register to it. For example, you have the data segment, the value is 1230 in hex, and if the source index has 0045 hex, then the effective address formed is what I told you, the 1230, which is the data contained in the data segment register, will be multiplied by 10 in hex, and that will be added with the content present in the source index, which ultimately gives 12345 as the address. So you are giving a 16-bit address in 2 registers, which is data segment register and source index register, but you get a 20-bit physical address. So the address thus formed with these two registers, you call it as an effective address. So by default, you can use BX, SI and DI register, which work very well with the data segment register. And similarly, the base pointer and the stack pointer will work with the stack segment register. So you have a special purpose register, which is the instruction pointer. This will always point to the next instruction to be executed. So in your 8085 processor, this is normally called as a program counter, which will be addressing to the next instruction. So the offset is always related to the code segment. And of course, this works together with the CS segment register, and it points to the currently executing instruction. And coming to the flag register, it determines the current status of the processor. So these flags are modified automatically by the CPU after arithmetical and logical operations. This determines the conditions to transfer the control to other parts of the program. So basically, the users cannot access these register directly. So you could see here you have 9 flags, and these flags are divided into two categories. One you call it as a conditional flag, the other one you call it as a control flags. So here overflow flag, direction flag, interrupt flag, trap flag, sign flag, zero flag, auxiliary flag, parity flag and the carry flag. So these are the conditional flags where the carry flag indicates an overflow condition for unsigned arithmetical operation. Auxiliary carry flag, it is used in the operations like BCD operations, where when a carry is generated from the lower nibble to the higher nibble, auxiliary carry flag will be set. You cannot test this flag, it is internally set. Parity flag is used to indicate the parity of the result. If the lower byte of the result contains the even number of ones, then the parity flag will set, else it will be reset. Reset means it will be a 0. 0 flag is set once the result is 0 after any arithmetical or logical operation. And coming to the sign flag, so the first bit of the byte or word is assigned as a sign bit. That is, you call it as an MSB bit. If the result of the operation is negative, the sign flag will be set. Overflow flag, it occurs when signed numbers are added or subtracted. Suppose you are not able to accommodate the sign bit in the MSB bit, then this flag will be set. Coming to the control flags, here you have 3 flags over here. One you call it as a trap flag, which is used for single step debugging. Suppose I want to see the error, I want to debug the error for every instruction at a time, one at a time, then this flag can be set. Coming to the interrupt flag, it is the interrupt will be enabled or disabled. If it is set, then the maskable interrupt of 8086 is enabled, and if it is reset, the interrupt is disabled. So you can automatically set by instruction STI, which is set interrupt flag, and you can reset by executing the clear instruction flag. Coming to the direction flag, it is used mostly in the string operation, and once this flag is set, it will be accessed from the higher memory address to the lower memory address, and once it is reset, the string bytes or word will be accessed from the lower memory address to the higher memory address. Thank you.